and charge Higgs interactions.
Okay, thank you for introduction. And today we'll introduce a new production mode of the charge Higgs called sensor charge Higgs pair production. So as you know, the keyword sensor is very important to the quantum theory. And especially I will focus on the bosonic decay mode of this sensor charge Higgs pair production. And in the hydromassive we'll see, and in the future proposed hydrogen we'll see. And this work is collaborated with Professor Kim and Zhong and also Owen based on this work, these papers. Okay. So firstly, as we know, the STEMMA is so successful, especially after we discovered the final piece, the Higgs boson, with the method of 125 GeV. So this is not a start of the research because we believe there are some new basics beyond the standard models. Okay, so what is a mission for the future client? For example, the 14 TeV update of the LC. So the first one is we can make a very precise measurement of the property of a Higgs boson. As a major, the morning section, Professor Kim has tell us if we make a very precise measurement of Higgs bosons, then there may take up some hint of a new basics. So for example, in this talk, I focus on the two Higgs domain models. So for example, some global fitting of this group, we consider all the channel, both the production and decay channel of two Higgs domain models. And I will explain what is the angle beta and alpha later, and what is the tangent beta. But here you just remember the angle, if the angle beta minus alpha close to pi over 2 means the alignment limit. And the alignment limit important means that one of the scalar bosons is standard model like. So all of the couplings is the same as the standard model predictions. So as you can see from this global fitting, except for the, here is a type 1, type 2, type X, and type Y, two Higgs domain models. And I will explain later what is a type 1, 2, X, and Y. But you can very easily see from the figures, except for the type 1, other type of two Higgs model almost agree with the alignment limit. So this is a very strong constraint for the two Higgs domain model. So the data suggests the two Higgs model preferred for the alignment limit. Okay. So another mission is if we can find some new particles in the LC, that will no doubt be a new basic hint. For example, 750 GeV or 28 GeV, if we can find a new particle, that would be great. Okay, so in this study, we want to find, if possible, that we can find a new electron natural Higgs or the singly charged Higgs bosons on the LC or in the future projects. Okay. So let me first review the charged Higgs boson production mode. There are various production modes in the LC. And in this talk, I especially focus on the fifth one, the sensor charged Higgs boson production. And this channel is very new. So this one is proposed from the Professor Sinya Kalamuna's group in this June. This process from the beta boson fusions with a W+, this is a sensor with a true forward jet. And the final step will be two sensor charged Higgs with true forward jets. Okay, so what's so special for this process? So for this process, you can see the Feynman diagrams here. For this final step, there are only this kind of T-channel process with the thermal Higgs, and then the capital H, and the capital A inside this T-channel Feynman diagrams. And in this study, we focus on the bosonic decay of this charged Higgs. Means the charged Higgs mainly decay to the W minus and light pseudoscalars here. You can see here. The bosonic decay mode. And I will tell you later, this production mode will sensitive to the mass difference delta m, the difference between the MH minus MA. So this production mode is very sensitive to export the mass spectrum in a 2 Higgs level model. And this is important because if we can know the whole mass spectrum of the 2 Higgs level model, then we know more about these models. And especially in this study, we consider line limit. As I showed you, this is based on the Higgs precision data. The data prefer this kind of alignment limit. And also we consider the light pseudoscalar, as I say, this can decay, the charge can decay to W and A with a mass about 300 to 100, 30 to 100 GeV, and consider mass splitting between 200 to 250 GeV. And I will tell you later, if the delta M is very small, means the compressed spectrum case, the position of this production mode will be almost equal to 0, very tiny. So only this production mode only sensitive to the large mass splitting. So here we consider the large mass splitting case from 200 to 250 GeV case. Okay, so this is our main purpose for these studies. Okay, so let me first introduce very briefly about what is the 2 Higgs level model. So as you may know, in a simplest standard model, we only have one scalar doublet. But in the 2 Higgs level models, they have two Higgs doublet, phi 1 and phi 2, with the hypercharge of 1/2. And in the most general renormalized scalar potentials, we can write down these forms. And usually, the M11, N22, and lambda 1 to 4 is the real parameters. And for some CP violation purpose, we can make the M12 square and lambda 5 to be complex. Okay. So here, we want to change from the interaction state of the scalar bosons to the mass eigenstate. So we need to rotate the mass eigenstate and interaction state. So for example, here we use the angle beta to rotate the G plus minus and charge Higgs. Here's a boson bosons to the physical, to the phi 1 star, phi 2 star, to the physical state, G star, G plus minus and H plus minus. So here is a rotation angle beta I introduced previously. And also for the rotation from the low 1, low 2 to the capital H and small h by the angle alpha. So after this rotation angles, we can rotate the interaction state to the mass eigenstate what we want. And here, the rotation matrix is showing here. And the tangent beta is defined after the ratio of these two phases. Okay, so finally we have 7 independent parameters and 4 for the mass. These 4 mass parameters, and also 1 CP mixing angle alpha and tangent beta, and finally 1 and 2 squares. And for the Yukawa sectors, in order to avoid the forever changing neutral currents, it's inspired from the Wamber and Gloshow's papers. They suggest there's a D2 symmetry. Phi 1 change after D2 go back to phi 1, the phi 2 will have a minus sign. So based on this D2 symmetry, they have 4 famous classification of the 2 Higgs models. So as you may know, if we just expand the Yukawa couplings, we have 4 different types of the 2 Higgs model called type 1, type 2, lepton specific and flip. And for the lepton specific and flip, sometimes they're called type 3, type 4, or type X, or type Y. So it's just a name. But you can see they're only for the D2 symmetry, there are only this kind of 4 classifications. Okay, and in the later I will focus on the type 3 and type 1 and type 3, and I will tell you later why we focus on these 2 models. Okay, so then we see the constraint of these models. So firstly, we need to worry about electroweak precision observable, especially for if we want to consider the mass splitting is so large. Especially for the oblique parameter S, T, and U. For the T parameters, it was sensitive to the isospeed violations. That means the mass splitting is very sensitive. If the mass splitting are too large, then it will violate the constraint of this EWPOS constraints. And usually, we fix the U equal to 0 when we consider this constraint. And we use the 2018 PDG reviews data, this one, for constraint. Okay, so here I just want to convince you that they still have some rooms. Yes, they still have some rooms for this kind of large mass splitting. The red part is exactly alignment limit, the psi beta minus alpha equal to 1. And the green colors is near alignment limit from the 0.97 to 1. So you can see they still have, sorry, the color is reversed. The red color is near alignment limit, and the green color is exactly alignment limit. So you can see for the near alignment limit, the red color, they still have some rooms for this kind of very large mass splitting between the capital H and capital A, the CP even and CPR scalars. Okay. So how about the basic constraints? So as you know, the basic constraint is very strong for the two Higgs subgroup model, especially for the type 2 and type 4. So roughly speaking, the constraint is more than the constraint for the charge Higgs is more than 580 GeV for the type 2 and type 4. So that is a partial reason why we don't consider type 2 and type 4 for this scenario, because the charge Higgs is too heavy. But for the type 1 and type 3, even we consider all these B2S photons, B2 mu plus, mu minus, and delta ms of the B mesons, once the tangent beta larger than 3, for the light charge Higgs from 100 to 200 GeV is still allowed. So that is the reason we focus on the type 1 and type 3, two Higgs double model for this light charge Higgs case. Okay, so here is a branching ratios. So in this branching ratio, I just want to convince you. So for the large enough tangent betas, even for the type 1 and the type 3 case, the bosonic decay mode, the charge decay to W and A can be the dominant one. So this is very important. Otherwise, if the branching is too small, then it's not so efficient to consider this mode. Okay. So another one is the decay branching ratio for the pseudo scalar, this light pseudo scalars. So for this one, for the type 1, as we know, is independent of the tangent beta. So the major one is decay to a D bar. And for the type 3, because for the total mode, for type 3 is a lepton-specific model. So means this coupling to the leptons is proportional to tangent beta. But for other fermions, is inverse to the tangent beta. So once the tangent beta enhances, so the total mode will be decay mode, will be the dominant mode. Okay, so here's a constraint from the LSC for the light charge Higgs. For example, here we consider a charge Higgs decay to tau nu, and the left-hand side is the type 1, and the right-hand side is type 3. Okay, I will not go into the details. I just want to tell you, I consider all the constraint of the colliders and other parts. And also, for LSC, the CMS group, they also consider this bosonic decay mode, the charge Higgs decay to A and W plus, and the A decay to mu plus, mu minus channels. And here also show you the constraint for the left-hand side type 1, right-hand side type 3. Okay, you can see for type 1 and type 3, because for type 3 is proportional, the coupling to the lepton is proportional to tangent beta, so the constraint is much stronger. Okay. So the main part of the talk is about the first part, the sensor charge Higgs pair productions. Okay, you can see the fundamental diagram here. If you consider the alignment limit, as I said, cosine beta minus alpha equal to 0, and you consider this subprocess, this one, W plus to the H plus, and in the alignment limit, the stem Higgs will decouple. So any capital H and capital A involved. And you can make very simply a calculation, and finally you find the amplitude is only proportional to delta M. So that's the reason why, if you consider the mass is degenerate, then this production coefficient is exactly 0. But if the mass splitting is large enough, then this production coefficient is very important and large, and very important to detect the LC. Okay, so here's a numerical result. We consider delta M equal to 300 GeV, 200 GeV, and 100 GeV. you can very clearly see once the mass become larger, the coefficient can be also larger. And here we consider BBF curve here. Okay. So here we make a signal and background analysis for the type 1 and type 3 two Higgs domain models. And we use the standard collider simulation tools for this analysis. And here is the four main standard backgrounds. And for the type 1, we consider signal pulses is about two BB bar pair come from the light pseudoscalars with two forward jet and two sensor leptons. So you can understand for this kind of signatures, it's very unique and very novel. So the backgrounds, it's very hard to find thermal backgrounds, but they still have some layers. So for example, you can see here's a cut flow tables for this one at 14 dBs. So we put some analysis code. So I will not show the details, explain the detail here, but you can see even our signal is about 1.3 over 10 minus 3 femtobar. The cross-section is really tiny, but the background is also tiny. And the signal to background ratio is about close to 1 to 1. So that is good. We have a good signal of the background ratio. But unfortunately, the cross-section is small, means we need more luminosity or more energy to detect this one. Also, so we also consider the high energy 27 TeV LC, and also high luminosity to see if possible we can detect these channels. Okay, here is our result. So you can see if the mass splitting is small, for example, 100 MeV, here Z is a significance. You can simply consider if a Z equal to 2 means a 95 confidence level 2 sigma. Okay, so you can see for this kind of case, if the mass splitting is small, then we cannot detect for this kind of case. But if the mass splitting is large enough, for example, for this case, the mass splitting is 200 GeV or 250 GeV. So large part of a parameter space can be detected larger than 3 sigmas. So it's detectable in the high energy luminosity for this kind of scenarios. Okay, similar for the type 3. So I will not explain for the type 3 because the strategy is similar. So I will skip. So the result for the type 3, the results a little bit better than the type 1s. But for the large mass splitting case, there can be all above the 3 sigma level. So I will try to convince you that in a high energy LC, it's possible to detect these channels in the future. Okay, finally I made conclusions. So in this talk, I want to show you a new production mode of the sensor charge Higgs production mode in these channels. And this production mode is very sensitive to the mass splitting inside the 2 Higgs models. Especially in this study, we focus on the type 1 and type 3 2 Higgs model. In the high luminosity LC and the high energy luminosity LC. And compared with the original work of the Professor Kawamura's papers, they consider mass splitting case of this one, but here we consider the light pseudoscalar case. So our work can be a supplement of their original works. So anyway, this kind of production mode, the sensor charge Higgs production mode, is sensitive to the mass splitting, also sensitive to the mass spectrum, especially for this kind of light pseudoscalar particles. Okay, here are some details about our numerical result. I will just skip here. And here's a take-home message for you about these channels. So thank you for your attention.
Some time for questions?
So you said that you come and do like a 3 sigma level.
Yes.
So then that's not a discovery.
Yes.
So suppose you see some 3 sigma, what do you
Three.
So yes.
Above 3 sigma. Yes.
So for 5 sigma, only this one, the blue line. Yeah.
So is there any consideration for the same sign charge Higgs production in inert Higgs domain model?
Because for the inner twist model, the final state will have missing energy, right?
Right.
So it's much difficult because you can see from our kinematic figures. This, for example, this maybe pack one is more easier to see. You can see we need to use the infinite mass cut to separate from backgrounds.
Okay.
Yeah.
Okay.
Other questions? Okay, now that's thanks.
Thank you.
The next speaker is